if I give you a complete background into how to basic I hope to try to get it, yeah, we're sort of using this. So next, how about norms? So B is a vector space of the reals and complex. It's a function that takes values in the reals that maps the vector space of the reals such that for every pair of x, y in the vector space, the norm is always positive or it's non-negative. With 0 it's only at x is 0. X is 0 this is not this vector space. You can multiply by the scalar distance outside of the modulus. And it's a triangle on the positive norm. And in fact, you can drop this condition. There's something called a seminorm, which is a norm without B. And if you don't have B as a condition, let's just ask what's the simplest seminorm? Well, actually it's this. It's not a very useful seminorm, but it is a seminorm. So it's our condition. This is true for all x. The seminorm in a sense, splits the space. If this function is a seminorm on this vector space, and a subspace of the vector space, all those vectors with seminorm with the norm equal to 0, then that's a subspace. It's called the null space of the seminorm. And if B1 is a subspace of this vector space with 0 intersection with this null space, then in fact you've got yourself a norm back again, a regular norm on this other subspace. In fact, you can define an equivalence relation. I can say x and y look exactly the same to me as long as this is true. Then the corresponding cosets, which is just the sets defined by this equivalence relation, they themselves form a vector space. And on that space, this is again a regular norm. So they're very closely linked, same norms and norms. This is an example on R5. I think you can see that. I can define a seminorm this way. The null space. Sorry, I have my vectors, which is transpose. The null space is found by these two vectors here. Okay. Now, a norm is a generalization of length. We're all used to this definition of the Tübingen norm in n dimensions. However, you can also have norms on infinite sequences. So now we've got LP. Where by LP I mean infinite sequences such that this thing inside brackets converges to 30. So I can define a norm this way. This sequence, that's not enough. There is a norm in P, and that's a norm in LP. And in fact, when finite sums across 2, it's the same thing, finite sums. And now we get to the things you see in the papers all the time. The L1 norm is also known as the Manhattan norm, because it's like a city block. And it's just the sum of the sizes of these individual values. The infinity norm, as P tends to infinity, it's just the max. It's actually a norm. It's not a continuous norm, but it is a norm. So a key thing is, when you see a norm vector space, sort of the quote norm vector space, it's two things. It's a vector space and a norm. And changing either one changes everything, or can change it. Okay, we're going to tie this together with, I'm going to talk more about norms, but before I do that, I have to introduce convexity. So you probably don't know what it is, just what open it. Let's come back to this in the convex optimization method. Conscious convex is between x1 and x2, where x2 is like to say. The function lies below core joining f1 and x2 everywhere. And it's strictly convex if it's strictly lies below. It doesn't function called anywhere except here. All such core, all such points x1 and x2 in the domain of this function. And just to write that mathematically, this is what we said. This is what you want to see. The function of the average of the points, roughly speaking, the weighted average, this point here, always lies below the average of the function, the weighted average of the functions. Now, the word convex is used for two separate units. It's also used for describing sets. A set is convex if for all points, pairs of points in the set, all points of the line joining in the set lie in the set. Of course, for this to be meaningful, you have to know what I mean by a line. The lying in the set. People generally don't define strictly convex sets. They just define open and closed sets. Okay, so now we can talk about norms a bit more, get a geometrical picture of what norms really are. So I introduced just now the L-infinity norm. Suppose I draw the one sphere, namely the surface mod x equals 1. I mean, norm of x equals 1. Where now norm is the L-infinity norm. What do I get? What's it look like? Well, I get a square. So, in fact, I've shown you a sphere equal to a square, which is the norm correctly. Square of the circle. Blue, the L2 is just a regular one. And green is the L1 sphere. And notice that each one fits inside the other. And there's something else that's interesting about these. They all are convex sets. If I take this green one, I can always choose a pair of points anywhere in the set. And every point on the line joining those 2 points also lies in the set. Now, you see, people sometimes use something they call the L0 norm. So let's talk about that. And there's a sphere across. So by the L0 norm, what they really mean is they just count the number of non-zero elements in the vector. So I give you a vector, it's got some zeros, got some non-zero. Everything that's non-zero, count them up, that's the L0 norm. Is that really a norm? Absolutely not. This is roughly what we mean. There's one of the keyness in here. If I take these goes to infinity, it goes to 0 here, this will become 1 given the symbol of 0. So let's just prove that the L0 norm is not a norm. So the field for Rn, or vectors in Rn, under the field R or C. It's very easy. We're just going to consider some scalar times some vector, the L0 norm. So this is true. This is certainly true if alpha is 0. If alpha is not equal to 0, this is true, because this doesn't change the number of non-zero elements. But it's not equal to the size of alpha times this, and there's alpha 1. So it cannot be norm. In fact, another way to see this on a norm is that this pointed across, because I've plotted all points in which one and only one component is non-zero. So you get cross this off forever. But this crosses on a convex set because all the points between this point and this point don't line the cross. So actually, we'll see in a minute, but that's another reason it cannot possibly be a norm. I don't want to squish L0 too much. There is a norm, an L0 norm, and we'll discuss that in a minute. But it's not this. It's a very different one. Okay, so I just told you that it's bad because it's not convex. Let's prove that all norms are convex. It's extremely simple, and sometimes people forget this and they go through long proofs and they just realize that this is true. So it's worth remembering. I'm going to show you that all norms are convex, no matter what the norm is. What I have to show you is this is actually equal to this, right? Well, this is equal to this by the triangle inequality of norms. And I can take this absolute value outside by the other multiplicative quality norms. And since this is positive, the absolute value is equal to itself. And the same is true with respect to this, is now between 0 and 1 here, by definition. So I've just shown that all norms are convex functions, no matter how complicated the norm, or strange, or it's true. And in fact, another interesting thing about convexity and why how to link convex sets and convex functions is that if you have a convex function, then if you imagine the region defined by this function being negative, or less than some constant, this defines a convex set. Something we do next week. So let's just quickly prove that. I have all x, where x is f is negative. This is negative and this is negative, and certainly, let's see. This is less than equal to this, right? Less than equal to 0. So this is also negative. Therefore, the points, all these points lie satisfy this efficiency. So they don't lie in the set, so the set is convex. And in fact, the unit ball, which is just in front of you those points, which the norm is less than or equal to 1, the sphere is where it lies on the surface, the ball is inside the sphere, including the sphere. For any norm, that must be a convex region. So you can just look at this picture right away and say, well, that can't be norm, because this is a convex region. And actually, there's another reason this is useful now, is that if you're doing convex programming, and you know norms are convex, you can have things like, this norm must be less than equal to C as a constraint, and you get a convex programming problem, which is very, very handy. And I'll describe this to you. Now, I'm going to tell you how to make your own norm just by painting a picture in a minute, but before I do that, I want to introduce a few more things. So there's a few more definitions. Just one slide first. I'm going to define open constant compacts. Let's do that. So given some norm, you can give me all you like, and some set in vector space. By an open set, I mean for any x in this set, there is some epsilon, which is positive, such that the open ball around x is in the set. An open ball is just the points for which the norm x minus epsilon modulus is estimated to, sorry, the points which lie within epsilon of x, using the norm, this norm. Okay? We can define a closed set to be just a complement of open sets. The bounded set means that it just has to lie on some sphere, some uniform, some norm, or some radius, not one radius, some radius. Now, compact is an interesting one. There's two definitions that I'm going to quickly go over. The first is that every sequence in your set, in order to be compact, for this set to be compact, every sequence must contain some subsequence which converges with its limit in the set. That's a very intuitive thing. You step along and convert through this kind of set. But there's another kind of weird definition, which we'll get back to in a minute. And that's this. A cover of a set, every cover of a set is a finite subtype. What does that mean? Well, here's my set. I choose some possibly infinite number of sets which cover the set, which means that the set itself lies inside the units of all these strange sets. Whenever I can do that, even if this is infinite, no matter how I choose, it must be true that there's a finite subset of these guys that also covers X. Now, that might seem as just, why would anybody want to make that definition? But what's very interesting about this definition is I haven't actually used the concept of distance anywhere. I've just used the concept of openness. We'll come back later to why that's important. But, okay, so a few developments about compact sets. Compact sets are closed and bounded. With finite dimensional non-vector spaces, every closed bounded space is not set of compact. This is not true for infinite dimensional non-vector spaces. Not for all of them. And then for a non-vector space, unit one is compact, is an interesting one. Then that vector space must be finite dimensional. Okay, so now we're in a position to build.
Shouldn't you say every open cover has a finite cover?
Yes. Yes, I'm sorry. These are open sets. Okay, so now you can make your own norm by just painting it, because this is theorem. Any symmetric in real finite dimensional spaces, any symmetric compact complex region, simple on the origin defines a norm. Even if you can't write down an equation that norm actually is, this defines a norm. By symmetric, I mean that the point lies on the surface and the negative point also lies on the surface. And so you can have strange shaped things, but they're very difficult to write down mathematically, so you know it's a norm. That might be useful. Okay, now we're in a position to rescue L0. We'd like to rescue this curve. So now let's go back to this tiniest field, Z2, just zeros and ones and ands and XORs, that's the two positive and additive functions. So now I'm going to consider n tuples, just vectors, n tuples of numbers, or not normal numbers, you can tell me it's not one. And then for a vector space, over the field, Z2. Because I can multiply them, I can add these guys with my XOR add, everything works great. This is the multiplicative inverse, and this is the multiplicative identity, which is 1. Now I'm going to define a norm, an L0 norm, to be that number of non-zero elements of X. Is that now a norm? Well, does it satisfy the norm conditions for this field? This is certainly true, the number of non-zero elements is greater than 0. It's also true that the number of non-zero elements is 0 only if everything's 0. It's also true now that if I multiply by something from my field Z2, which is 0 or 1, I can bring it outside. If it's 0, certainly this is 0, but it is 0. If it's 1, I'm just doing an and, which is also an. So now it works. And finally, as an exercise, if you have two vectors with 1s and 0s sprinkled through each vector, then the number of 1s and 0s of the XOR of the two vectors always has to equal to some, just check that. So now we have an L0 norm. Just isn't defined as real, it's defined as Z2. So here's some puzzles to throw out. We're living in Z2. Z2 only has two elements, 0 and 1. So how on earth can I have something, the number of non-zero elements, if we're bigger than 1? Can we do it? So what's that mean? What's that play? Right. I talked about addition. These are very simple puzzles. What's subtraction? And now I have to really, well, I'll tell you what this one is. I have two vectors, I want to know distances, so I have to define subtraction, which is the inverse of addition. And if you just figure this out, that is the number of elements by which x and y disagree. So we've got the regular or computer science having distance between two vectors. But we have to go to the special case Z2 for it to work. Now, there's something interesting about norms, and that is that every inner product gives you a norm. If it's not true, that every norm gives you another product. So how does every inner product give you a norm? Well, you start with your inner product, you just plug in the same thing twice, take the square root, it turns out that satisfies every condition you need for the norm. It's some sort of triangular quality of the grid. It turns out that for real vector spaces, a norm has a corresponding inner product, which gives the norm this way. If and only if, I'm sorry, let me bring back up a second. Let's see. Does every norm have an inner product? If it's true that it has an inner product, if for real vector spaces, it must be true that this is the inner product. You think, okay, now I've shown you how to get an inner product from a norm, right? I just defined to do this. I mean, if you think of this as the inner product of x plus y with x plus y, and that's the inner product of x minus y, and the xx cancel, and the yy cancel, and you've got 2xy minus 2xy, or minus y by 4 to get this. However, this doesn't work always. It turns out that the necessary and sufficient condition for a norm to correspond to the inner product is this parallelogram identity, which is saying that this is x squared plus this x squared after this these two. And this is pointed out by Jordan and Lyman in 35. Okay. So now we're going to talk about, again, people use RP norms all over the place in these papers. Right? So we're going to talk about those. Let's actually think about which LP norms can be defined as inner products. So I'd like to find an inner product that gives me an LP norm. What is an LP norm? An LP norm by uppercase L, I mean a norm of this form. Now I have an integral. Lowercase l, I have a norm that this is a sum over a sequence of elements. Now I'm just depending on functions. So LP norms are norms defined over functions. In fact, it's defined this way. But this has to be an integral object. So it's defined over things of integral. So for example, the L2 norm is this. And I'm asking, when can I find an inner product that gives me this quantity? So, for general P, not just for this too. When can I find something like some inner product? You can find anywhere you like, as long as it satisfies the inner product rules, right? So we're going to try to, let's just choose something that seems to make sense. I'm going to define fg to be f times g modulus raised to the p over 2 integrated raised to the p. Because there's a square. Then it's sort of linear, except there's a modulus here, which should be outside the lambda, so that's a bit of a problem right there. So it's sort of 90% satisfies the linearity rule, with p not equal to 2. But it doesn't satisfy this rule, this linearity rule, p is not equal to 2. It does if p is equal to 2. If p is equal to 2, I can drop this modulus sign, and I just get the opposite upside. Well, I've shown you a particular choice of inner product that didn't work. Now let's prove that no inner product works. Or p not equal to 2. So I'm going to try and do it fairly intuitively. So, okay, that wasn't very smart. Maybe there's something else that's smarter that would work. Keep everything for 1. So now I'm not going to use the parallelogram rule, but I'm going to use the fact that if the inner product exists, then this must be true. Also. direction from just cutting these out in the product vector space. And I'm going to choose two particular functions. I can choose any function I like. This is actually a proof, but it's very sort of sketchy. My blue function looks like this: 1 and then 2 and then 0 everywhere else. My red function looks like this: 0 everywhere except between 1 and 2, where it's 1. And I'm going to see if one of the conditions for the inner product holds, just plugging in what the inner product must be if this long can be derived from the inner product. Okay? So if I do this, and I plug in and I integrate, it's easy to integrate over the box function, using a 1 and 0, 2 and 0. Then I get this one. On the other hand, if I take the lambda outside this inner product and integrate, then I get this one. So, well, I want these to be equal to any p or some. It's not inner product without p. So I'm going to plot these two figures. I'm going to choose, it doesn't matter what we choose arbitrarily, I'm going to choose now equals 1/2 here actually. And the only cross of 2, which means that this is essentially a proof, at least with p less than equal to 10, that the only norm, the only LP norm associated with the product is the L2 norm. Okay. So we sort of stripped under the rug the infinity norm. It's kind of a weird norm. Let's do that directly. And now we're going to just directly use the parallelogram law to prove that the infinity norm on Rn has no inner product. So to do that, I just have to find an example that doesn't work with that parallelogram test. So it's that parallelogram test that doesn't prove the infinity norm is derivable from the inner product. And just plugging in, remember the infinity is the max. So the max of x plus y 2, max of x minus y is also 2. You get modulus, so you get this. On the other hand, this for that hand side. The right hand side, you get 1 here, but 2 here squared. 4 not being equal to 5, we've just proved the max infinity norm has no product. And of course, you can extend this from R2 to any R, so embedding the example that I just gave you. So I just wanted to give you a feel for what's going on. What's happening is, maybe you've got another product, you've got yourself a norm. And I can give you norms for another product. Okay, now to get to Hilbert spaces, I need to do a couple more things, and we'll do that. Hilbert spaces. I need to define a Cauchy sequence. What is a Cauchy sequence? It sounds kind of interesting. It's a sequence of vectors in your norm vector space. Just a vector space equipped with some defined norm. So the Cauchy sequence is for every positive epsilon, there's some number, integer n, such that these two guys get closer and closer together. They never get further apart than epsilon, everywhere beyond n. So here's my sequence. The Cauchy sequence condition is that these guys, 1, 2, 1, 1, 1, cannot ever get further apart than epsilon. Why is that useful? Why not just define convergence? We don't have to do convergence. Well, I think the key idea, you never see this written down, but I think this is the key idea. The key idea of the Cauchy sequence is you can define notions of convergence without ever leaving the space. Suppose you're walking along and you see footsteps. And you think, oh, those are footsteps. I think they're a sequence. I think they converge to something. And you follow the footsteps. But you get to the edge of the cliff. You prefer not to go over the cliff, you can help. You can define, with a Cauchy sequence, you can find out whether or not this converges without jumping over the cliff. Okay. So a few notes on Cauchy sequences. Every convergent sequence is a Cauchy sequence. So in a sense, it's a generalization of convergence. Not every Cauchy sequence. Every convergent sequence is Cauchy. Not every Cauchy is convergent. Here's an example of a Cauchy sequence that's not convergent. And you can define the space of polynomials. Any polynomial you choose to define on the interval 0 through 1. And I'm going to choose the max norm. That's a perfectly good norm in the space of polynomials. Max value of the polynomial takes on interval. I'm going to define the sequence. My sequence is going to be this. The nth element is the sum from 1 up to here. Probably recognize this in the sum. Then this is a Cauchy sequence, because these guys never get further apart than I think they satisfy the Cauchy condition. But it doesn't converge, because its limit is not described as a polynomial. In this space, it's left the space, it's somewhere else. Who knows what actually, well, you don't know. It's not a polynomial. Note that to define a kosher sequence, you have to say what norm you're going to be in. Okay. One more notion and then we're done. That's the notion of completeness. So now that we've defined this kosherness, I don't mean by completeness. Non-vector space is complete. Okay, so the non-vector space is complete, but every such sequence in this space converges to another in this space. It's got no holes, it's got no cliffs which you can fall. You're very safe. Any convergent sequence, you're always in the same. Kosher. And what's a Banach space? It's a complete norm space. The definition of a Banach space. So for example, Rn, the usual completeness space of the P norm, is complete for all P greater than 1. Fractional P is allowed. Sequence space RP is complete also. Okay. By CAB here, I mean the space of continuous functions. Any continuous function you choose, but only defined on its support between A and B. P is greater than A. That would be an interesting one. This with the L infinity norm is complete. But with the L2 or the L1 norm is not complete. How can that possibly be? Well, basically what's happening is with the L2 or L1 norm, you can take the sequence of continuous functions and get closer and closer and closer and wind up with something that's not continuous until you're outside the space, you've got what to do. So that is a lot. Completeness depends on the choice of norm. Space is the same in the sense that the set is the same. The set of continuous functions. But the norm is different. All square integrable functions are L2 norm in a complete space. Another interesting thing. We've got L2 norm here, a complete space, and L2 norm here, that's not complete. So because the square integrable functions contain these continuous functions, we sort of say, if we enlarge the space a little bit, now we need to complete the same thing. A complete space contains all its third points, just so I can explain it. And the kind of nice thing about completeness is if you're stuck with a space that's not complete for some reason, you can always just complete it. You can always say, I'm going to add in the minimum number of points needed so that every kosher sequence converges to a point in that space. Okay. So now we can define these two spaces. Now that you've got all the machinery, this is very easy. Hilbert space is just completing the product space. It's happening. It's a vector space, equivalent to the product. The inner product always gives me a norm. I use that norm to define a kosher sequence. Every kosher sequence converges to something in space. The space is complete, it's constant. It's basically a well-defined inner product, a well-behaved inner product. So we can draw this little picture. By the end, I'll have a picture of all possible cases you can imagine. I hope to get to the end. Polynomials on the zero or the maximum. I'll just show you it's not a complete space, but it is a norm space. So all the Banach spaces are norm spaces, and all Hilbert spaces are inner product spaces. They're a subset, actually. And also, for continuous functions, the L2 norm is not a Hilbert space, it is a continuous function only. It's also not a Banach space. So there's the point that's in here. It's a strange place. Spaces that have inner products that are not complete. So now we can draw a nice picture. So think of the space of all possible norm vector spaces. I think of the space of all possible Banach spaces, and the space of all possible Hilbert spaces. So in the space of all possible Hilbert spaces, we've already been through all of these examples. I'm just summarizing them. Finite dimensional inner product spaces by Hilbert spaces. L2 for all square integrable functions are also complete spaces. We have this chart. And sequences, the L2 sequences, are also Hilbert spaces. I've shown you that continuous functions, with the L infinity norm is okay, but not with the L2 norm. But this is still a norm space. Polynomials of 0, 1, which are not complete. And finally, the LP not equal to 2, we just proved actually that there's no inner product, so we can't be Hilbert spaces. But they are Banach spaces. Because they're norm spaces, they're norm vector spaces. In fact, they're complete ones. Okay, so that's kind of a useful thing to come to the back of your mind when Hilbert spaces, Banach spaces, and norm spaces fit together. Now, as I told you already, I like to always try and say how many kinds of thing there are to understand it. So let's ask how many kinds of Hilbert spaces there are. Sounds like a silly question, of course, it's probably intimidating. There's all sorts of different kinds of Hilbert spaces. They're a bit intimidating, but I want you to be not intimidated. So, let me make the following. I have to make a definition before I can show you why answer this question. So suppose you've got two spaces E1 and E2, vector spaces, and a mapping. And it's called a linear mapping if this is the case, as you'd expect, where these are elements of the space and these elements of the field, or in this case space. So we've got two Hilbert spaces that are isomorphic to each other. If there's a one-to-one linear mapping from one to the other, such that the dot product takes exactly the same values when you do this mapping, this magic mapping between the Hilbert spaces. And such a mapping, a linear mapping, one-to-one linear mapping, is called a Hilbert space isomorphic. So it means they're essentially the same beats. They may look different, but they're the same. So now we can answer this question. How many dimensions of Hilbert spaces are there? Okay, one more definition. I'll go there. Hilbert space is called separable if it contains a complete orthogonal sequence. And in fact, finite dimensional Hilbert spaces are considered separable. There's another definition of separable which is a little less easy to get your hands around. That Hilbert space contains a counter-dense subset. So let's look into that. So it's basically that you can have an infinite orthogonal sequence. For example, these are separable Hilbert spaces. Most people only work with separable Hilbert spaces. So now we can answer this question. If H is separable, if H is one of these Hilbert spaces most people tend to use, then there's two. That's it. If H is infinite dimensional, then it's isomorphic to this L2 Hilbert space. And if it's finite dimensional dimension n, then it's isomorphic to Cn. So it's two kinds. Okay? So that's kind of nice. If we boil down several Hilbert spaces, it goes two kinds of. Okay, now I'm going to. When am I supposed to put it? It's like 12+6. Okay, so maybe 10 through. Okay. I'm going to go through the Riesz Representation Theorem. Again, you see this in papers, and it's a very basic theorem, so I want to just describe it. It's not the same thing as the representative theorem people use to describe Hilbert spaces, but it's an important theorem. So let's just go through this. So what do we got by a functional, a linear functional non-vector space, which is this coupled vector space and sphere. It's a linear mapping which takes the vector space into this sphere. Now the operator norm of the linear functional is defined with this. That's just the modulus. You look at the unit sphere with this norm, and you look at the maximum value of this modulus. That's defined with the norm vector. It's called an operator norm. And I also have to do what I mean by bounded before I can tell you the Riesz Representation Theorem. So I define operator norm, I define functional. The reason it's called a functional, not a function, it originally arose because people were having entire functions to numbers. I think that's the accent. So by bounded, I mean a linear function on all vector space is bounded. It's very intuitive. If this is bounded by some constant times norm of x, now this is just a modulus, but this is the Hilbert space norm for all x in the vector space. If and only if this is true, if and only if the operator norm is finite. So, but I've got two things here. I've told you what bounded means, and I'm figuring out a theorem about boundedness. This is finite and it's bounded. So now the Riesz Representation Theorem says that you have one of these bounded linear functional on a Hilbert space H. And there is exactly one element of your Hilbert space such that f is equal to the inner product of x, such that x is the inner product of x, with this magic x limit. It's just one of these, exactly. For all x. And the operation on the f is equal to the Hilbert space of norm of this x zero. So let's just do an example. I'm going to prove it, but it's proof it's sure I'm going to do an example. I'm going to choose a Hilbert space of square integral functions. Okay? So A, D, A integral. I'm going to define a linear functional like this. Just going to try it out. So let's first of all check that it's a linear bounded functional because it satisfies the conditions of the theorem. It's certainly linear because if the boundary x plus 3 y, it's just integral, right? So I can take the random mu out and just constant. So nice and linear. Sounded a little trickier. The size of that is by definition this. You can start to find out. And that's just a of a triangle. Okay? It's just a complement of two different things here. Now I can just plug in, well, that's the scope of what I'm saying. And this is by definition a normal vector. So yes, bounded, f of x, or what is that equal to some number as a normal vector. There's one thing left we have to do. We have to find x0 or 2 bits. Find x0. That's actually easy. I'm going to show you what it was. It's this one function. If I plug this in, then my inner product with any x equals this, which is exactly that. So that was kind of trivial. But what about slightly less trivial? What about this other Hilbert theorem? That the operator norm of x is actually equal to the Hilbert space norm of x0. Okay, let's look at those. Hilbert space norm of x0 is by definition this. 1 is x0 is just this one function. It's take its square root and differentiate, take the square root. That's the definition of the Hilbert space norm for L2. And that gives you what I'm saying. The operator norm is this. Remember? I take my unit sphere with this special norm, whatever it is, doesn't matter. It's unit sphere. And I find the sum. Well, just plug in what f is this, right? So what I'm trying to solve is this. Find the sum, actually it's a max, of this quantity subject to the norm of 1. And actually, it's not now exercise for students, because I've given you the machinery you need to do this using the Lagrange multipliers. And we've got a practice of directions. So it's quite doable. And this is the answer. So, in fact, yes, indeed. We do. Okay. So now, don't worry, I'm not going to spend just a couple more slides actually. And I want to cover all the kinds of space I like to have this. So I have just a couple of slides on metrics and 2 on topological spaces, and that's it. Symmetric space. Getting more and more general as this lecture winds down. Okay, metric space, for any set, some function defined on the set of pairs of elements with range in the reals, defined on this product space, and ordered pairs, pairs up in the order, that gives it E, and it's found these 3 conditions. Rho of xy is finite, real number, for every pair, that makes sense. It's equal to 0 if only these points are the same point. And rho of y is less than rho of xy plus rho of xz, or xyz in this setting. Well, people are probably wondering, here's the puzzles for it. So aren't metrics always supposed to be positive? And what about symmetry? Are they supposed to be symmetric? And where's the triangle point? What about it? It's quite the same thing. The puzzle is, prove these 3 things from these 3 things. So in fact, everything here is contained in this definition. So a metric is a very general idea compared to norm. Every norm gives you a metric. How? Well, just find this. Just got triangle positives for every element. Metric space is much more than not a picture of things containing things. Here's an unusual metric space, one that's used by mathematicians recently, actually, to quantify how close a space is to Euclidean space in some sense. They define metrics of trees. So here's a tree. Each leg of the tree has a number. And the metric is just the distance between this point and this point. Distance from this point and this point. It's the shortest path, it's the shortest path point. Don't forget a metric. In fact, you can think of metrics as extending the notion of continuity in the following sense. If you define continuity for me, choose any epsilon right, form a ball around f of x, and that's the ball, then you can find a delta, such that the delta ball around x maps inside of this. It's a funny way to define continuity, but it's actually useful. Let's look at metrics just one more slide. So, some metrics on function spaces. So now I've still got sort of all bounded functions in reals. Now this is a perfect good metric. Actually, all of these have good metrics. And the reason is that they come from norm. So in fact, you can find a key metric. Well, here's a slightly different metric. It doesn't come from norm, but okay. I haven't tested that. By CR of AB, I mean functions that are defined on the interval AB, and for which at least R derivatives are defined. 0, 1, 2, 3, R derivatives are. If I can define a metric as this, it's sort of an infinity metric, it's a max metric, but it's also got an R parameter, and it's defined to be the biggest of these quantities. Absolute difference of f1 is g, absolute difference of f1 is g prime, etc. That's Don't forget that. So you can define all sorts of bizarre metrics. Right, this is the last space. One more slide after this, and that's it. So now, even more general than metric space is topological space. Topological space is a pair. It's a set and a collection of subsets. It's incredibly simple. And that's all it is. With these conditions, the whole set and the null set are in the set of subsets. Okay, the elements in S. The intersection of any two sets in S is also in S. And the union of any collection of sets in S is also in S. And this will be an infinite. Now S is called topology for this set A, and the members of S called open sets, T. Well, here's a curious thing. I've got two definitions of open sets. I just sort of randomly arbitrarily said these are open sets. You choose anything you like, you call them open sets, it's fine. But then you've got this other version of openness, which we've got earlier on, which is like the open ball that never actually reached the edge. Yeah. So I'll see that hang for a second. Then more general metric spaces. So every metric space is topological space. How's that? I take all the open sets defined by the metric. Once an open set defined by the metric, it's a ball. So that the distance, the center of the ball is the accessory to R. I define those open sets to be open sets by topology. That's a perfectly topological space. That means that every metric space is topological space. Okay? Every set, actually, is metrizable. It's a sort of trivial metric. I say 2 points, the distance between them is 1, they're different, and 0 for the set. It's called a discrete, it's called standard discrete metric. But in fact, not every topological space is metrizable. So that means, what that means is, despite the fact that I can metrize any set, when I give you a topological space, I have to define all these open sets. For that to be a metrizable topological space, I have to find a metric that gives me those open sets as its open sets. And it's a metrizable topological space. So in that sense, topological spaces are more general than metric spaces. And in fact, it's a metric that's simple continuity, except topological spaces. So here's a new definition of continuity. So you're given two topological spaces, T1 and T2, the map from A1 to A2. Then when defining this map to continuous, if for every open set in A2, the inverse image of this set is in A1. So we've slid something very subtle in here. We've defined openness and continuity without defining distance. There's no norms involved. So this is kind of exciting. Topological spaces are trying to be more general in that sense. Okay. Final slides. Hilbert spaces and their places. So now, Hilbert spaces are inner product spaces that are complete. Every inner product corresponds to a norm. So norm complete spaces contain Hilbert spaces. But there are norm complete spaces that do not have an inner product. So Banach spaces contain Hilbert spaces, right? But there are norm spaces that are not Banach spaces. There are metric spaces that are not norm spaces. There are topological spaces that are metric spaces. So you can help them up in generality. Just to give you one example of a space that's topological but none of the others, is something called an indiscrete topology, where you just take really sort of the primeness or the prime least prime topology. Just the set itself and a null set is your set of subsets. And if this set itself contains more than one point, then it cannot be empty space. So I just wanted to show you how this picture of increasing generality is. Right, thank you very much.